Hello, everyone. My name is Abe from the University of Michigan, Dearborn. First, I'd like to start by thanking all the audience here today, the organizers, my advisor who is here today, and our collaborators from SRI International and the University of Chicago. So, as you all know, millions of internet users around the world are being subject to censorship. This is like a global and real-world problem that has attracted human rights activists. And more importantly, it has pushed research into discovering censorship evasion tools and censorship measurement tools. Research efforts were primarily directed into manually discovering evasion strategies and censor-side bugs and vulnerabilities through hypothesis and fuzz testing. Later on, researchers were able to automate the process by leveraging AI-based techniques like genetic algorithms. What all of these efforts have in common is that they all require repeatedly probing the sensor, which increases the detection risk on the sensor side. And as a direct example of this threat, lately, China is started blocking UNI. And this is the first and the main concern of this work. The second concern is how can we protect these users that are using these censorship evasion tools from being detected? Starting with the first concern, we found that the sensor can train a machine learning model to detect client flows that contains malicious packet manipulations that are intended for evasion or for censorship measurements. In a more detailed manner, the sensor can collect network traces of a target censorship evasion tool, extract relevant features, such as TCP flags, TCP payloads, etc., and train classic machine learning models like tree-based classifiers, support vector machines, etc. And the output here is whether a client's flow contains malicious packet manipulations. However, to avoid false positives, the sensor needs a higher level of detection to decide whether to block a client. For that, the sensor can leverage hypothesis testing through the threshold random walk algorithm that has been primarily used for port scan detection. The TRW is needed to make a blocking decision based on multiple flow level detection observations returned by the machine learning model. And this is how it works. It increments a vector Y of flow level detection observations and use it to compute the likelihood value that the client is benign compared to the probability that it is malicious. And the IP blocking decision is made only if the likelihood value is lower than threshold eta 0. Here, the thresholds eta 0 and eta 1 are selected with respect to the detection probability that is offered by the machine learning model. The other case is when the likelihood value is higher than eta 1. This means that the client is most likely benign. However, in this case, we want to keep scanning for future potential malicious flows. So we reset the likelihood value with respect to previous observations. And in case the TRW wasn't able to converge into a blocking decision, it just automatically waits for future observations. To test this real-time detection approach, we leverage one of the latest state-of-the-art censorship evasion tools called Geneva. It stands for genetic evasion. It is a genetic algorithm that repeatedly probes the sensor to produce censorship evasion strategies. And like any other genetic algorithm, it has building blocks to compose first generation of strategies, and then through mutation, it evolves into higher generations. And by testing each strategy directly against the sensor, it computes their fitness function and punishes the less fit strategies. Geneva has 4 building blocks. It can duplicate a packet, tamper with its TCP IP header fields, fragment IP, segment TCP, or just drop the whole packet. And a Geneva strategy is composed of a trigger and a set of actions. If we consider this example, this strategy is triggered on any outbound TCP ACK packet. It duplicates the packet, so we end up with 2 duplicates. The first on the left side of the tree is sent without any manipulations, and Geneva tampers with the TCP flags and IPTTL of the one on the right side of the tree, and then send it. Geneva was reportedly able to find 31 new working strategies in China, 6 in India, and 11 in Kazakhstan. Despite all of these impressive results, The real-time detection approach based on machine learning and TRW that we talked about earlier was able to block Geneva clients with 99% confidence after only 2 observations, which means after only 2 sensor probes made by Geneva. This is exactly why it is important to study the detection risk of these tools. Geneva was easily detectable because it produces an unusual network traffic. For instance, it has a high number of overlapping TCP segments, a high number of corrupt data offset fields, and we found that it has many invalid TCP flags. Now, let's suppose that the client is trying to probe the sensor. The first probe will be detected by the machine learning flow level detector, which means the likelihood value of the TRW will get closer into making a blocking decision by getting closer to the threshold eta 0. If the client continues to blindly probing the sensor, the TRW will most likely converge into a blocking decision. Instead, our intuition through DeResistor is simply to pause the probing phase by leveraging detection feedback. More precisely, since the first probe was detected, then we stop the probing phase and we switch to wait for normal traffic. And just by waiting for one normal flow, the likelihood value will get back and away from the threshold eta 0, and now it's safe to resume the probing phase. Following the same approach, the likelihood value will be encapsulated between 2 thresholds, disabling the TRW from making a blocking decision. And finally, this will allow tools like Geneva to finish their probing phase and training without being blocked by the TRW. In this illustration, the DeResistor waited only for one normal flow. We call it the jump size. However, it is equipped to be configured with a higher jump size. Now, this is how the probing phase will look like when we use DeResistor. The per-flow detection feedback is provided by a local machine learning model. It is incorporated in DeResistor setup, and we call it FDeResistor. Now, if the client is specifically trying to run Geneva with DeResistor, an additional layer of protection can be made by punishing detection in the fitness function of Geneva. This will force Geneva into making more detection-resilient strategies. Now, let's talk a little bit about some of the promising results of DeResistor. We ran Geneva with DeResistor in one of the 3 well-known censoring countries. We set 3 vantage points in China, 1 in India and 1 in Kazakhstan. And we assume that all sensors are running the real-time detection approach that we talked about earlier. The evaluation goals are first to check whether DeResistor is able to protect Geneva from sensor-side detection. And second, whether Geneva is still capable of reaching successful strategies when deployed with DeResistor. So here are the results. While Geneva is blocked after 2 observations, when deployed with DeResistor, it was able to finish its training phase without being IP blocked. And this is observed in all 3 countries across all 5 vantage points. If we look into DeResistor traces, we notice that improving the fitness function actually helped to decrease Geneva detectable features like segmentation and corrupt data offset fields. And all of this is achieved without sacrificing Geneva's ability into producing strategies with high success rate in all 3 countries. Now, as a countermeasure, the sensor can try to update its model by training it on previous cycles of DeResistor. This means that F-sensor will be more accurate than FDeResistor, and it might lead to blocking FDeResistor. To regain the upper hand, DeResistor can be reconfigured either by retraining its local model, similarly to the sensor, or by making sure that the probing phase is paused after every Geneva attempt, regardless of whether we have a detection feedback from FDeResistor. By doing so, we found that FDeResistor is still able to protect Geneva, even after another cycle of F-sensor update. As another countermeasure, the sensor can try to filter out normal traffic that are introduced when DeResistor pauses the probing phase. This can be done by estimating the jump size J. On the other hand, DeResistor can randomize the jump size J after every Geneva attempt. within the option of length Jmax. Now the censor will have to estimate the value of Jmax, then the value of J. So we experiment the three cases when the estimation is lower, equal, and higher of the actual value Jmax. And we run each experiment 3 times. No IP blocking was observed for all 3 experiments across all 3 runs, which means that DeResistor was able to overcome this countermeasure by randomizing the jump size J. Now the censor can take a whole different measure and chooses to substitute the TRW with an additional machine learning model for IP-level detection. This can be achieved by training an LSTM model to decide whether to block a client based on a sequence of consecutive flow-level detection observations of size L returned by F-sensor. We found that an LSTM trained with L equal 10 can reach a detection accuracy of 99.63% on DeResistor with J equal 1. But the accuracy degrades as we increase the value of the jump size. As a counter move, the censor can deploy an LSTM with a very high value of L. But this is not effective because it will delay the blocking decision until at least L observations has been made. And this is regardless of whether DeResistor is deployed. In this context, we find the TRW to be more efficient because it does not require a fixed length of sequence L. Instead, it makes a decision as soon as a high confidence is reached. Through this work, we draw the following conclusions. First, we showed that it is extremely necessary to put research efforts into the detection risk of anti-censorship tools. And we proposed DeResistor as one of the first steps toward detection resilience of censorship, evasion, and measurement. We provide our code and artifact publicly available for those who are interested. And before I finish, I just want to announce that I'm currently in the job market. So for any recruiters here, please come find me later on. Thank you for your attention.